Hello everybody, myself Prashant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. So in the last class of our power electronics and drives, we have started a new our topic, that is inverter, and we have discussed with the primary introduction of what is inverter and what are the different types of inverters. So this classification was based on different basis. Particularly we have classified them as per their input source, commutation technique, circuit configurations, and wave-shape of output voltage. And then we have discuss about the operations of a single phase half phase inverters with resistive load, and of course with resistive inductive load and purely inductive loads also, and particularly their operations, their waveforms, etc. Today we'll discuss about operations of single phase full wave base inverters, basically how it operates and how its circuit is being formed. All these things will be discussed here. Single phase full wave bridge inverters circuit is shown here. It is the single phase full bridge DC to DC inverter with resistive load, basically, and this inverter then taken into the following conventions, assumptions and conventions. So before going to these assumptions and conventions, we will definitely say that these full bridge inverters are consisted of two pairs of controlled switches, S1 and S2. Here it is Q1, Q2 and Q3 and Q4. So it is S1, S2 and S3, S4, and two pairs of diodes, basically D1, D2 and D4. So among these devices, only one pair of devices conduct simultaneously, and when switches S1 and S2 are on, the output voltage across the load is positive, and similarly when the switches S3 and S4 are on, the output voltage across the load is negative. And diodes D1, D2, D3, D4 are used as feedback diodes, and the load of the full bridge inverters will be either resistive or inductive. So the sequence of the operations of the switches and diodes for resistive load and RL load like this. For resistive load, sequence is S1, S2, first pair, then S3, S4, again S1, S2, then S3, S4. And for RL load or inductive load, so either say D1, D2, then S1, S2, D3, D4, then S3, S4, again D1, D2, S1, S2, D3, D4, S3, S4. So this is the sequence of operations. Once again I am telling you. So basically this full bridge inverters consist of two pairs of control switches, S1, S2 and S3, S4, and two pairs of diodes, D1, D2 and D3, D4. And among these devices, only one pair of devices conduct simultaneously, and suppose when switches S1 and S2 are on, the output voltage across our load is positive, and when switches S3 and S4 are on, the output voltage across the load is negative. So, and diodes D1, D2, D3, D4 are used as a feedback diodes, and the load for the full bridge inverter will be either resistive or inductive, or basically RL load. And the sequence of switching of the switches and the diodes for R and RL load like this, respectively. For R load, it is S1, S2, then S3, S4, again S1, S2, then S3, S4. And for RL load, because of this inductor, so sequence of operations will be changed, basically it will store energy in the inductor. So this will be D1, D2, S1, S2, D3, D4, then again S3, S4, D1, D2, S1, S2, D3, D4, S3, S4 in this fashion. So let us start and with this description of the circuits and with certain assumptions and conventions, that is the current entering this particular node A is say considered to be positive, and switches S1, S2, S3, S4, so it is either Q1, Q2, Q3, Q4 are unidirectional, and that is they conduct current in one directions only. Okay, so this is the circuit diagram of a single phase full bridge AC DC to AC inverters with this resistive load. Now when this switch S1 and S2 are turned on simultaneously, as I told you, during the duration 0 to T1. Okay, so this S1 and S2 are turned on simultaneously during the duration say 0 to T1. The input voltage is Vn appears across the load, and the current flows from say points A to B. And in that case, this Q1, Q2, that is switch S1 and S2 on, and this Q3 and Q4, that is S3 and S4 are off, and the output voltage will be positive, say the source voltage and Vs, and this is the path actually, and this is these two switches are on. Okay, so this will be like this. Clear? Once again I'm showing you. See, this switch, this is switch, this suppose it is S1, it is closed, so in that case from this switch current is going to this load. Then again this is switch S2, this is on. Okay, this will complete the path. Clear? And the voltage appears across the load. Since the current is flowing from A to B, so it will be this source voltage. Okay, this is the output voltage, will be equal to source voltage, this is Vs. Clear? Now suppose switch S3 and S4 are turned on during the duration T1 to T2, capital T1 to T2, and the voltage across the load is reversed, and the current through the load goes from B to A. So in that case, the switch Q1, Q2, the S1 and S2 is off, and Q3 and Q4 is on. Okay, so the voltage across the load will be output voltage from here. Current is flowing from B to A, and it will be minus Gs, or the source voltage. So see, this is the path. Okay, so see, this is the follow this path. Okay, this is switch 3, S3 or Q3. This is closed. So current here coming here, there this node B, it can't go here because this is off. So this is the load, current is flowing from B to A. Then this switch S4, this is Q4, this is closed. So this is the path. Okay, follow this path. Don't be confused, because these diodes are not conducting, because they are in reverse bias conditions. Okay, so this is the path. So current is flowing from B to A. So as a result, the load voltage will be say minus Vs. Okay, so if you the voltage and current waveforms across the resistive load will be like this. This is voltage waveform. This is for switch Vs1. This is for Vs2. This is for Vs4, etc. Okay. Clear? And this is IL1, this is IL2, this is IL3, and so on. Okay. So actually this is the voltage and current waveform. Clear? So I think you have understood this operations and the waveforms of pattern like this. Okay. This is the yellow. Clear. Now we'll discuss single phase full bridge inverter with RL loads. Should I repeat it? Okay, I'm once again repeating it so that you can understand. So before going to the discussions, I'm telling you this single phase full bridge inverter circuit is consisting of say two pairs of control switches, and that is S1, S2. Here it is Q1, Q2, and S3, S4, that is Q3, Q4, and two pairs of diodes, that is D1, D2, and D3, D4. So among these devices, only one pair devices conduct simultaneously. When switches S1, S2 are on, the output voltage across the load is positive. Similarly, when switches S3, S4 are on, output voltage across the load is negative. And diode D1, D2, D3, and D4 are used as feedback diodes. The load of the full bridge type inverter is either of resistive load or inductive load, so you can say RL load, and the sequence of switching of the switches and the diodes for resistive and RL load will be like this. Resistive load S1, S2, S3, S4, again S1, S2, then S3, S4, in this fashion. So here S1 means Q1, S2 means Q2, S3 means Q3, and S4 means Q4. And for RL load, so it will be D1, D2, then S1, S2, then again D3, D4, S1, S3, S4, D1, D2, and S1, S2, D3, D4, and then S3, S4. So because this change of sequence is due to the presence of the inductance. Okay. So basically I shown this is the circuit and this is the operational criteria when say S1, S2 is on for the period 0 to T1. So this will be the current path. Okay, this will be the current path, and the load voltage is positive, this source voltage. And when S3, S4 is in this time S3, S4 was off, and when second case, when S3, S4 is on, so during this time capital T1 to capital T2, and then S1 and S2 is off, that is Q1, Q2 is off, and Q3 and Q4 is on. So in that case, sequence of operation will be like this. See, actually what you are finding here, actually this current direction has been changed. Initially for the first case it was from A to B, and second case it was from B to A. So as a result, the load voltage will be say of opposite polarity. That means magnitude is the same input voltage, but the polarity will be different. And the voltage and current waveforms across the resistive load is shown here. See? So this is all about the single phase full bridge DC to AC inverters with resistive load. Now I think it is clear. Okay, so now we'll discuss about the single phase full bridge inverter for a load or inductive load. So basic operation sequence I have already discussed actually, and single phase square wave voltage source inverter, as I told you, that produces square shaped output voltage for a single phase load, and such inverters have a very simple control logic, and power switches need to operate at much lower frequencies compared to switches in some other types of inverters. And the very first generation inverters using thyristor switches were almost um, invariably square wave inverters because thyristor switches could be switches on and off only a few hundred times in a second. And in contrast, the present day switches like IGBTs are say much faster and used at switching frequencies of several kilohertz, and single phase inverters mostly use half bridge or full bridge topologies, and power circuits for these topologies uh, is shown here. That is like this. This is the power circuit for single phase full base DC to AC inverter with inductive load. And this topology is analyzed under the say assumption of ideal circuit conditions, and accordingly it is assumed that the input DC voltage, that is if it is DC, it is constant and the switches are lossless. So in full base topology has two such legs. Each leg of the inverter consists of two series connected electronic switches like this. And so these are the series connected electronic switches, and these are the two legs. This is one leg, this is another leg. These are the series connected switches. So two switches in each leg. Okay, and each of these switches consist of IGBT type control switch. Echo switch is an uncontrolled diode is put in anti-parallel manner. Okay, this is the uncontrolled diode connected in anti-parallel manner. These switches are capable of conducting bidirectional current, but they need to block only one polarity of the voltage. And the junction point of the switches in each leg of the inverter serves as the output point of the load. See, this is the junction point of the switches, and these are the output point of the load. Okay, and I am telling once again this for this inductive load, the sequence of operation will be like this. If you start with S1, S2, then S1, S2, then diodes D3, D4, then again S3, S4, then D1, D2, say, then S1, S2, then D3, D4, then S3, S4, then again D1, D2, and so on. So, as I told you, this single phase, full phase inverters with resistive and resistive inductive load, basically the inductive load. So we have discussed, and also we have discussed different topology of power circuits, and how why thyristor instead of thyristors nowadays IGBTs are used as a switch. What are the advantages that I discuss? Now we'll discuss on different types of inverter, series inverter, parallel inverters, etc. So this is the block diagram of a series inverter. Okay. Series inverter circuit. In series inverter, the commutating elements is L and C connected in series with the load. This is L, this is C connected in series with the load. This is L, and this is C commutating element for this connected in series with the load. Okay, So basically, it continues the series RLC resonance circuit. Okay, and the two ACRs, actually this ACR one, that is T1, and this is ACR 2, or is T2, are used in to produce the halves, that is positive and the negative half cycles in the output. Okay, so as I told you, L and C are connected in series with the load used as a commutating element, and as a result, in both the cases, this is the thyristor 1, ACR 1, and this is thyristor 2, or ACR 2. This is the commutating element for T1, that is this L1 load and C1, and this is L2 load and the C2 for thyristor 2, or this is the commutating elements. Two ACRs are used to produce the halves, that is positive and the negative halves of the output. And since this LC is connected in series with the load, so it constitutes a series RLC resonance circuit. Okay, and in the first half of the output current, when ACR 1 is triggered, that is thyristor 1 is triggered, it will allow the current to flow through like this, L1 load, and that time C2 will be charging, it will be like this, C2 will be charging. Okay, and the capacitor C1 is already charged at this instant, discharges to ACR, and now it is discharges to this ACR1. Okay. What we have seen, so when this thyristor T1 is triggered, so current path will be like this. Okay, and since C1 is already charged, so during this time it will discharge us to this ACR. Okay, it will be discharged like this. Okay, and as a result, the 50% of the current is drawn from the input source and 50% from this capacitor. So 50% since they are in resonance circuit, so 50% from source and 50% from this capacitor C1. Clear? So similarly, in the second half, when this thyristor 2 is triggered, the output current C1, this will be like this. Output current C1 will be charged. And C1 will be charged, and C2 is will discharge. Okay, to the load like this. Okay. This is the discharge part of the C2. This is the charging part of C1. So because after the completions of when this thyristor will be off, so this will be discharged fully, and when this is triggered, so this will be charged in this fashion. Okay, and output this C2, which was charged in the first case, will now discharge in this one. Okay, so again, so the same say topology or same sequence of operations is being followed. So basically, 50% of the say load current will be drawn from the source and 50% from the capacitor C2. Here, so that is 50% from the DC input source and rest from the capacitor. So the ACR T1 and T2 are alternatively fired to get AC voltage and the current, and then there is the beauty of the series inverter. Okay. Now, for parallel inverters, I think the single phase parallel inverter circuit consists of it's also two issues, T1 and T2, and inductor L and output transformer and the commutating capacitor C. And the output voltage and the current V0 and I0 respectively. And the function of the inductor L is to make the source current constant. And during the working of this inverter, a capacitor C comes in parallel with the load via the transformer, so it is called a parallel inverter. Okay. C. This is the capacitor. I mean, parallel with the transformer. So that's why it is called, say, parallel inverter. Okay. So it consists of, once again I'm telling you, two HCRs, HCR1 and HCR2, or you can say T1, T2, whatever you want to say. And an inductor, an output transformer, and a commutating capacitor. Inductor, output or commutating transformer, and load. Okay. So basically, these are connected in parallel. Okay. So actually, see, this capacitor, inverter, capacitor C comes in parallel with the load via the transformer. C. So this transformer is connected in parallel. That's why it is called parallel inverter. So this is the circuit diagram. See it very clearly. This is transformer. This is load. Load is connected to the secondary of transformer, and this capacitor is connected in parallel with this load via this transformer. So that's why it is parallel inverter. Okay. And here the operations of this inverter having like this, mode 1, then mode 2, mode 3. And in the first mode, HCR1 is conducting and the current flow in the upper half of the primary winding of this is HCR1 is conducting. Current is flowing in the upper half of the primary winding. Okay. And HCR2 is off. This is off. And as a result, an EMF Vs is induced across the upper half as well as lower half of the primary winding. Okay. As a result, in other words, the total voltage across the primary winding is 2 Vs. Now the capacitor C is charged to a voltage is 2 Vs. And with the upper plate as positive. Okay. And in the second mode, at the time T2, at that time transistor 2 is turned on by applying trigger pulse to its case, and at this time at T equals 0, capacitor voltage 2 Vs appears across the reverse bias across transistor 1, and it is therefore turned off. And the current IO output begins to flow to T2 and lower half of the primary winding, and now the capacitor has charged that is plate plus 2 Vs to minus 2 Vs. So in mode 2 operation at time to T2 is turned on by applying a trigger pulse to its gate, and at this time T0 or T equal to 0, capacitor voltage 2 Vs appears across as a reverse bias across thyristor 1, and it is therefore turned off, and the current I0 begins to flow through thyristor 2 and lower half of the primary winding. And the capacitor is charged upper plate as negative from plus 2 Vs to minus 2 Vs at time t equal to T1. And load voltage also changes from Vs at t equal to 0 to minus Vs at t equal to T1. And in mode 3 of operations, when capacitor is charged to minus Vs, thyristor 1 may be turned on at a time when T1 or thyristor 1 is triggered. Capacitor voltage 2 Vs applies a reverse bias across T2, and it is therefore turned off. And after T2 is off, capacitor starts discharging and charge to the opposite directions. The upper plate is positive. So that's all about the parallel inverter. Once again, I'm repeating the operations of the parallel inverters like this. Actually, parallel operation of operation of the parallel inverters. This is a single phase inverter circuit consists of two SCRs, that is T1 and T2, an inductor L, and output transformer and the counterweight capacitor C. And output voltage and the current are V0 and the I0 respectively. And functions of the inductor L is to make the source current constant, and during the working of this inverter, capacitor C comes in parallel with the load by the transformer, so it is called a parallel inverter. And its operation has three modes. In the first mode, thyristor 1 is conducting and the current flow in the upper of the primary winding. Thyristor 2 is off, and as a result, an EMF PS is induced across the upper as well as lower half of the primary winding transformer. In other words, the total voltage across primary winding is 2 Vs. Now the capacitor C charges to voltage 2 Vs with upper plate is positive. In the second mode, at time t to 0. Actually, at time t equal to 0, the thyristor 2 is T2 is turned on by applying a trigger pulse to its gates, and at this time t equal to 0, capacitor voltage is 2 Vs appears as a reverse bias across T1, that is SCR1. It is therefore turned off, and the current I0 begins to flow through thyristor 2 and lower half of the primary winding. Now the capacitor is charged, upper plate is negative from plus 2 Vs to minus 2 Vs at time t equal to T1, and load voltage also changes from Vs at t equal to 0 to minus Vs at t equal to T1. And in mode 3, when capacitor is charged to minus Vs, thyristor 1 may be turned on at any time when thyristor 1 is triggered, and capacitor voltage 2 Vs applies a reverse bias across thyristor 2, which is therefore turned off. And after thyristor 2 is off, capacitor starts discharging and charge to opposite directions, and the upper plate is negative. So that's all about this operations of the parallel inverters. Once again, I'm telling you, you must with this lecture you must follow your textbook, whatever you have with you, whether it is Linda or Rashid or any good book. And still you find any difficulties, you may contact me, as I told you before. So thank you. That's all for today, and hope you have enjoyed the class. If you have any problem, you definitely discuss with me later on, either by phone, WhatsApp, mail, whatever medium you can pick up. So that's all. Thank you very much.